Hi everyone. In this session we're going to look at system services. We're going to look at linkers and loaders, and then we'll finish off with a discussion on operating system design and implementation concepts. So first off, we'll look at operating system services. We've talked a little bit about this already. I'll just reiterate some of the concepts that we've looked at. I'll discuss the idea of linkers and loaders using a diagram, why applications are operating specific, operating system design and implementation concepts. First off, though, let's take a look at system services. So all modern operating systems provide system services, so a set of utilities. And these type of utilities are slightly different from operating system to operating system in how they're implemented. But conceptually, we need to have file management, so the ability to create, delete, and copy files. We need to have a way to keep track of status information. So performance information and logging information. For example, in a Mac operating system, we could look at Activity Monitor for performance reporting. And in Windows, we could look at Resource Manager to see how our system is performing. Also, the ability to modify files, so to be able to make changes to files in our system. Also, some sort of programming language support, so to be able to support compilers and to be able to support debuggers. Also the ability to load programs and execute programs, and that includes the ability to debug. Then also communications, so you should be able to create virtual connections. And then background services like networking. Of course, every operating system these days should provide an ability to access the internet, for example, so through some sort of a web browser, connect to resources that are available over the internet. All right, let's talk a little bit about linkers and loaders. So with linkers and loaders, to run on a CPU, a program must be brought into memory and then placed into the context of a process. So we basically start a process, for example, using the fork command in Unix-based systems. So a number of steps can occur from compiling a program to placing it in memory. And so this example over here on the right is showing this process. So we start off first with a source program, so a piece of code that somebody has written. And these source files are then compiled into what are called object files that may be loaded into any physical memory location. So we first compile and we create an object file. A linker, which we see here, a linker, then combines these relocatable object files into a single binary executable file. So the object file here and any other object files that are relevant for this particular source program. So the linker does that. Then we come up with an executable file that's created. Once we have an executable file, then a loader is used to load the binary executable file into memory. And it can now be run on a CPU core. And so when a program name is entered on the command line, the shell, using dynamically linked libraries that are relevant for that particular executable file, the shell creates a new process using fork as an example. So that's how a file is linked together and loaded. So just to reiterate then, source files are compiled into object files that may be loaded into any physical memory location. The linker then combines these relocatable object files into a single binary executable. And then the loader is used to load the binary executable file into memory, so it can now be run on a CPU core. And then when a program name is entered, so when we go to the command line and we type in the name of the program, the shell creates a new process. Okay, so a process is created, and as an example, using a Linux command, fork. If we're using Windows, it would be a different command, for example, create process. Now, most systems allow a program to dynamically link libraries as the program is loaded. So we saw that in the previous example. And Windows goes through a similar set of steps, and it supports what are called DLLs. So within the Windows operating system, there are a number of DLLs that are available for programs. And the advantage to this approach is that it avoids linking and loading libraries that may not be used. And it also allows for multiple processes to share these libraries. So reusability can occur here. And of course, if we were using these libraries, these dynamically linked libraries, that optimizes memory usage. Let's take a look then at operating system specific applications. So fundamentally, applications from one system are not executable on other operating systems. So as we have now seen, each operating system provides different utilities and features that make this not possible. So when you go online, for example, and you're using Mac OS, and you want to download an application, you have to find the downloadable file that is specific to that particular operating system. So if you're downloading for Mac, it's going to be a different downloadable than if you're downloading for Windows. Each operating system provides a unique set of system calls so that we need to have a version of that application that makes the right system calls, that accesses the right API for the operating system that we're running that application on. So then the question might arise, well, then how does MS Word run on Mac and Windows? Well, they're actually two different applications. So they can be written in an interpreted language, for example, Python. And they can be written to include a VM container. So for example, Java. So we have what's called a JVM, or a Java virtual machine, where an application can run inside of that, what they call a sandbox. And can be written using standard APIs, but it still needs to be ported to each operating system. So somebody has to go in and actually make sure that the API calls are correct. And developers for MS Word have done that. So they've ported the application MS Word to Mac OS X systems and also to Windows systems. So they're essentially two different applications. Some cross-application challenge. So other challenges that also exist between operating systems that don't allow applications to be run on more than one. Each operating system, for example, has a specific binary format. So the layout of the header, the instructions, the variables are different from OS to OS. CPUs also have varying instruction sets. So operating systems provide system calls that vary then from operating system to operating system. So we've seen that those system calls are named differently, for example, between Windows and between Linux/Unix. Now, when we're designing an operating system, there's some considerations. We talked a little bit about this earlier, the idea that user goals are different than system goals. So the user view, what a user expects and wants in an operating system, are different than what the system design goals are. So users want the system to be easy to learn. They want it to be easy to use. They want it to be reliable, and they want it to be safe and fast. From the system side of it, if you're developing an operating system, there's similar goals. For example, easy to design, easy to implement, and easy to maintain. So maintenance is a design goal that a user might not be concerned about, right? So they want the system to be fast. From a developer's perspective, though, when you do updates and new versions, you want it to be easy to go from update to update, from version to version. And also, you want the system to be able to maintain itself easily. So from a developer perspective, from a system perspective, the operating system should be flexible, it should be reliable, error-free, and also efficient. Another thing that users won't necessarily be concerned about is the idea of memory management, right? So if efficiency has something to do with, how much memory is used for particular system calls or for particular system processes. So efficiency is definitely a concern during operating system design. And you can see that both the user design goals and the system design goals are vague, which is why there's no unique solution for designing a particular operating system. Another concept is the idea of separating policy from mechanism. So mechanisms determine how we actually do something, whereas policies determine what will be done. So separation of these two ideas is important for flexibility. Now, policies are likely to change over time. So as a general flexible mechanism that works across many policies, a general flexible mechanism is preferable. So as an example, A mechanism for giving priorities should be flexible to allow for the changing of policies about the order of priorities. So just that's something you need to keep in mind. From an implementation perspective, it is difficult to make even general statements about how an operating system is implemented. So early operating systems were written in assembly language. Assembly language is a very low-level language that allows you to use very little memory allocation for your code. So code can be very efficient in assembly language. Now most operating systems are written using C or C++ and other higher level languages. And this makes them quicker to code and easier to port, but at the expense perhaps of memory usage. So at the expense of size and then also at the expense of speed. Now after the system is written and working, bottlenecks can be identified and adjusted. And so you can see with operating systems when you have one, a lot of updates come out. As the operating system is used and as certain issues are discovered, updates are put out by the operating system designers and developers, and these bottlenecks can then therefore be identified and adjusted. All right, so that's all I want to talk about in this session. So just to summarize, we looked at operating system services. We looked at linkers and loaders, so how we can dynamically link libraries when a program is loaded. We also looked at why applications are operating specific. So, for example, each operating system provides different utilities and features, and also a unique set of system calls. And then lastly, we looked at some operating system design and implementation concepts. All right, thanks for tuning in.